Well, thank you very much for the invitation to join you today. I'm going to tell you a little bit about the development of a solar system-wide internet, and then give you some sense for what we think the future holds in the exploration and eventual commercialization of space. But let me take you back to can you go to the next slide, please? This is the first very important test of the internet. In 1977, then we had three networks that were being linked together. One was a mobile packet radio net in the San Francisco Bay Area. The other was the ARPANET, which was the predecessor to the internet, which was operating in the US and Europe. And then a satellite network, packet satellite network over the Atlantic, linking the west coast of Europe to the east coast of the United States. I was the program manager for the internet project in the Defense Department, and this was our demonstration that the TCP/IP protocols actually worked in a live network environment. If you go to the next slide, this is just a picture of what the internet looks like today, although honestly, this is actually a 1999 rendering of the backbone forwarding tables of the Border Gateway Protocol. But it serves to illustrate that there are literally tens of thousands of networks in the internet. They all interact with each other based on whatever hardware and software the operators choose to use. It's all decentralized, except for assuring unique assignment of internet addresses and domain names, which is done by the Internet Corporation for Assigned Names and Numbers. Everything else is fully decentralized. Everyone chooses who to connect to and under what terms and conditions. The business models vary from nonprofit to government operated to commercial for-profit. And it all works because they've all adopted the same protocol suite. Next slide. So now let me take you back to 1997, when after 20 years, well, in 1976, two landers arrived at Mars, Viking 1 and 2, from the US. And that 1976 landing was a huge milestone. And then nothing worked for 20 years. Literally everything failed until 1997, when a successful Pathfinder project landed a small rover on Mars. Go to the next slide. So the Sojourner is the little 1997 robot that landed. There have been several others since that time, and I'll come back to that. In fact, if you go to the next slide, you'll see quite a large number of rovers have landed on Mars in the intervening period since 1997, most recently Perseverance and the Ingenuity helicopter. All of these have essentially spawned a great interest in some of us anyway, in developing an interplanetary backbone network to support manned and robotic space exploration and eventually commercialization of space. Next slide. So at the very beginning, after the rover landed in 1997, a small group of us got together at the Jet Propulsion Laboratory in Pasadena, California, to talk about what we should be doing in preparation for for what we think we would need 25 years later. So then this was in 1998 that we started this discussion. It turned out that we began thinking our way through the possibility of an interplanetary backbone. And while we were developing the ideas, the Spirit and Opportunity rovers landed on Mars in 2004. Some of you will remember in January. The original design had data coming from those two landers, those rovers, at 28.5 kilobits a second from the surface of Mars back to what's called the Deep Space Network, which is a big network of 3 70-meter dishes that are in Madrid, Spain, in Canberra, Australia, and Goldstone, California. And they, of course, being 70 meters, were capable of receiving very, very weak radio signals. However, the radios on board the rovers overheated. And of course, the engineers said, well, we have to back off on the duty cycle. And the scientists became even more grumpy than usual because they said, well, we won't get as much data back as we wanted. And it's only coming at 28 kilobits per second anyway. So they were not very happy. Then one of the engineers at JPL pointed out that there were X-band radios on the rovers, and there were also X-band radios on orbiters that had been sent before the landers arrived to map the surface of Mars to figure out where the rovers should go. So it was proposed to reprogram the rovers and the orbiters to essentially send data from the rovers up to the orbiters when the orbiter got to the right place overhead, and then have the orbiter hang on to the data and store it until it gets to the right place in its orbit to transmit data to the deep space net. Now, it turns out that the orbiters were not very far from the rovers, being only a few hundred miles. And so they could transmit data at 128 kilobits a second. And because the orbiters were outside of the atmosphere of Mars and had bigger antennas and solar power, they were able to transmit data to the deep space net at 128 kilobits a second. So we ended up doing store and forward, which is packet switching, in order to get the data back from Mars. And that particular method has been serving the Mars research teams literally ever since 2004. So it's a prototype of the store and forward network. Some of it was very manual in terms of control of when the transmissions happened, either up to the orbiter or from the orbiter to the deep space network. If we go to the next slide, we began talking in 1998. This is before the 2004 arrival. And we thought, well, maybe we can just use TCP/IP. The internet works on Earth, so maybe it'll work on Mars too. And then we started doing the math. It turns out the speed of light is too slow. If you look at the distance between Earth and Mars, while we're in orbit around the sun, when we're closest together, we're 35 million miles apart. That means it takes 7 minutes for a radio signal to go round trip from Earth to Mars and back. And when we're farthest apart in our orbits, relative orbits, it takes 40 minutes round trip time to go from Earth to Mars and back. Well, it turns out the TCP flow control mechanism does not work with 7 to 40 minutes of round trip time. And there are some other little problems. For example, if you were trying to do a domain name lookup, if you're on Mars and you're trying to figure out what's the IP address of the target on Earth and you want to do a domain name lookup, it's going to take you up to 40 minutes to get an answer back if you're lucky and didn't lose any data. And then by the time you get the answer back, the target may have moved to a different IP address because it was mobile and it had, it was using radio links to get to the internet. So we couldn't use the real internet design for interplanetary communication. Oh, there's another little problem. The planets are rotating and we don't know how to stop that. So if you were talking to something on the surface of Mars and it rotates, you can't talk to it until it comes around on the other side, just like, the orbiters. So we ended up saying, okay, what we have is a highly delayed, variably delayed, and disrupted communication environment, and we need to tolerate those variable delays and disruptions. That's a class of network which had not been built before. So the delay and disruption tolerant networking, or DTN, was the target of our new design. So we developed a new set of protocols we call the Bundle Protocol Suite. We do domain name resolution effectively. First, we figure out which planet we're going to, and then after we get there, after the packets arrive at that destination, then we figure out where to go, and, for example, from Mars to Earth, and then after we get to the Earth base station, so to speak, then we figure out how to get to the destination somewhere on the planet. And so that's a delayed name resolution technique. We also had to worry that because the links between the various parts of the system could go away because of planetary motion or because of orbital motion, we had to store data in the network until the links come back up. We don't do that in the internet, partly because back in '73, when the internet was designed, memory was expensive. And we didn't really need to do that kind of storing because we had such increased connectivity. We had a pretty resilient system with alternate paths available. But in this interplanetary system, the paths are much less rich. And therefore, we decided we would store data in the net. I mean, if you wanted to go to Jupiter and you'd gotten to Mars, you don't want to throw the data away, which is what we would do in the internet case, if the link to Jupiter from Mars wasn't up. In this case, in the bundle protocols, we hold the data at Mars in this case and then transmit it when the Mars-Jupiter link is available. Also, we discovered that network management is very different in a highly variably delayed environment. Ping is not your friend, where normally if you ping something on the internet, you get an answer back in about half a second or less. And that tells you that the destination is available. So you build your whole network management scheme around that idea. But if you're not going to get an answer back for 40 minutes or more, and you may even lose the data before it gets retransmitted, you need a very different kind of network management mechanism. So we had to develop that. And then finally, I was very concerned when the project got started that we be as secure as possible, because we didn't want a headline that said 15-year-old takes over MarsNet. So we built into the bundle protocol suite strong authentication and strong cryptography in order to make sure that all of the devices could recognize each other, and a foreign device would not be able to break into the network. And similarly, we wanted to make sure that we kept confidentiality, because in many cases you don't want somebody attempting to generate a command, for example, that would mess up one of the instruments or the relays in the network. Let's go to the next slide. So I'm not going to go through every single one of the bullets on this, the succeeding slides, except to say that we have been testing and refining the delay and disruption tolerant bundle protocol suite for ever since the 2004 period, actually ever since 1998. And so you can see that we've tested it with vehicles that are spacecraft that are still out in space, like the epoxy mission that used the Deep Impact spacecraft to visit 2 comets. We have been on the International Space Station since 2009, and in fact, we continue to work well beyond the 2018. It's on this slide. We did a real-time test, thanks to the European Space Agency, to control a rover that was in Germany from the International Space Station using the bundle protocols to show that despite the fact that they were designed for delay and disruption tolerance, that if they are in a low latency environment, they could be used to steer in real time a little rover, just like an astronaut who was in orbit around Mars might be using these same protocols to steer a rover around on the surface. We also were interested in high-speed communication, so we did a laser communication test. We had a spacecraft orbiting the moon, and we had a laser transceiver that could receive a signal at 622 megabits a second and bounce it back to Earth. So we were very happy to show that the protocols will work at high speed as well as at low latency. Next slide, please. There have been subsequent tests going on, and also concurrently a great deal of work testing interoperability among different implementations of the bundle protocol suite, and standardization, both at the Consultative Committee on Space Data Systems, which is an international organization made up of all of the spacefaring countries, and also the Internet Engineering Task Force. So they both have the same protocol suite. They both standardize them. They both publish those documents. And now we're ready to implement commercially if that's required. They're all open source. The protocols and their implementations are available on SourceForge at the moment, and will probably move to GitLab sometime in 2022. We also have a very interesting DTN test up in Luleå in the northern part of Sweden. The reindeer herders, the Sami reindeer herders, have put transceivers on the necks, around the necks of the reindeer that wander around in the forest. And we're using the delay and disruption tolerant protocol methods in order to capture the data about where they are. And then that information gets relayed back to a central location so they can keep track of where the reindeer have gone. So it's another example of implementing delay and disruption tolerance. In this case, there's a lot of disruption because the reindeer move around and their connectivity changes over time and goes away, of course, from time to time. Next slide. So there is an interplanetary networking special interest group, which is part of the Internet Society. You can see its website is ipnsig.org. You will find at the URL that is in this slide a report that we turned out in June of this year describing a strategic view of the development of an interplanetary backbone network spanning over a period of about 100 years. And so I would urge you to, if you're interested, to go and have a look at that report. It's a short report. It's only about 50 pages long, and a lot of it's got pictures. And so there isn't a huge amount of text, but it gives you an idea of how we are thinking this system could evolve. In fact, at the next slide, you'll see, I know that these are pretty tiny, so it's an eye chart. But the point I want to make here is that we begin probably with a backbone network, which is mostly made up of participants from the governmental space agencies. And then as the commercialization of space happens, and you're seeing it literally live today with SpaceX and Blue Origin and others, putting spacecraft in orbit, putting communication satellites in orbit, planning a return to the moon, the Artemis and Gateway programs in the US and others from other countries. We will see a mix of academic and government and commercial networks all needing to interconnect with each other in the same way that the internet interconnects multiple networks. And then eventually, we think in maybe 100 years from now, most of the communication system will be commercially supplied in the same way that most of the internet is a commercial operation today, some 50 years since it was originally designed. Next slide. So, of course, having thought our way through what we imagine the scenario of interplanetary networking would be, we decided we should look at the possibility of sending a spacecraft to Alpha Centauri, which is 4.3 light years away. And in order to understand what the challenges are, I went to the Lincoln Laboratory near MIT and asked if they would help us analyze what it would take, what the challenges are for getting a spacecraft to Alpha Centauri and transmitting data back. And there are three main problems. The first one is propulsion, because it takes, with the currently available rockets, it would take about 76,000 years to get to Alpha Centauri. That's a pretty long time to wait for the spacecraft to deliver some results back, considering that that's 7 times longer than our civilization has existed, if you consider 10,000 years ago to be the beginning of modern civilization, if you like. So propulsion is a big issue, and probably some kind of an ion engine will be needed at very much higher thrusts than we currently have in order to get that journey to happen in 100 years as opposed to 76,000. So propulsion is one challenge. The second challenge is navigation. And you can imagine, when you send a spacecraft to someplace around our solar system, it's very typical that part of the way to the destination, there'll be some mid-course corrections. And typically the delay for interacting with the spacecraft is measurable on periods of minutes to hours to even perhaps a day. And that's almost interactive, if you like. So we can control the spacecraft and give it advice about how it should do mid-course correction to get to the correct orbit or trajectory to achieve its destination. But now imagine for a moment you have a spacecraft that has gone a light year from Earth on its way to Alpha Centauri. It takes 1 year to transmit any kind of data to the spacecraft and another year to get the information back. That's not exactly interactive. So mid-course corrections may not be terribly feasible, and you may need to have an autonomous navigation capability for the spacecraft that's on its way to Alpha Centauri. There has been some speculation that using pulsars, some of which may be in another galaxy, but are very consistent in their rate of signaling, flashing, could be used as a kind of a galactic GPS system. In fact, instead of geo positioning, it becomes galactic positioning. So it might be that the system could do self-navigation using the pulsars as the control for where you are, calculating where you are on your journey to Alpha Centauri. Then the final problem is getting information back. How do you transmit the data back, and by what means should you do it? Should you use a laser? Should you use a radio? And I want you to think for just a second about what the implications are of being in orbit around Alpha Centauri, trying to figure out how to send data back to Earth about what you found there. Well, remember, you're 4.3 light years away. What that means is that the laser or the radio antenna that you're going to use to transmit the data back has to be aimed in the right direction so that by the time the signal gets there 4.3 years later, there will be an antenna in the right place to receive it. Well, that means figuring out where to point the antenna so that you know that the Earth is there, or maybe something in orbit around the sun is there to receive the signal. Just imagine how hard that calculation is going to be, trying to correctly and accurately predict exactly where to point the antenna so that the signal will, when it arrives 4.3 literally years later, it hits the right antenna. So that's a big problem that has not yet been fully solved. I think if you go to the next slide, that may be the last one. And this one is a fantastic presentation by one of the scientists at the Lincoln Laboratory who led the study on the challenges for an Alpha Centauri mission. And sort of summing everything up, he said that we're 53 dB away from being able to solve all the problems. And just in case you don't notice, 53 dB is on an order of a factor of 100,000. So that's a big deal. So that's where we are up to the minute on the interplanetary space project. We're all looking forward to the use of the bundled protocols in the Artemis and Gateway missions to return to the moon, and hopefully they'll be put to use when we finally start launching missions to Mars. So I'll stop there. I'll thank you very much for your time. Hope this generated some interesting thoughts, and I'm happy to answer questions about this or anything else that you might have in mind.